Okay, thank you. All right. So I guess what I want to talk about today is what can AI or machine learning do for science. In general, the tasks that we have, at least some of the tasks that we have, are how to generate data, simulated data, how to do inference, statistical inference, and how to do anomaly detection. Those would be, some of the main tasks that we like to do when we think of machine learning or AI for science. These are different tasks, and so they would have different algorithms, at least training algorithms. But I'll talk about, but they can also be combined in a single method, and I'll talk about a little bit about this. What are some of the goals that we want to achieve in scientific analysis is to do what we call optimal data analysis. But the question is, what does optimal mean? And you can define optimal, for example, as achieving the smallest possible error on certain things that you want to measure. So, so basically you want to have the best outcome of scientific discovery. But maybe optimal also means that you want to be the most robust against, I don't know, systematics in the data, either unknown systematics or known systematics. And then finally, some people at least believe that we also need to have some kind of trustworthiness in terms of being able to explain why is it that our data analysis is providing the results and why these results are perhaps better than some traditional baselines that people have used. All right, so let me start with introduction to AI, but I'll go quickly through this. All right, so just, quick example of what is AI and what are the topics that are discussed at the typical machine learning conferences. For example, you have generative models that people have talked a lot about these days. You will have optimization, you have probabilistic inference, Bayesian methods, Monte Carlo methods, trustworthiness, robustness, and applications. Okay, so I'll try to cover most of these, the things that are in squares, I guess I'll try to cover in this talk. Now, the AI practitioners are mostly from computer science and statistics. However, there is a growing community of people at intersection between AI and domain sciences. And they come from both directions, right? Some people have traditionally been trained in machine learning and now are interested in domain science applications, and vice versa. Some people that had traditionally been trained in domain sciences, such as physical sciences, are now developing methods, machine learning methods to analyze their scientific data. Again, for the purpose of this talk, AI and ML is the same thing. I guess the recent trend is that people like to use AI. So, okay, so let me go into a little bit more detail. What is the goal of AI in physics or physical sciences? One of the typical goals is data inference. So this again is the task where you're given some data and you want to infer some parameters from it. Let's call the parameters y and the data x. But in physics, at least we want to do more than just infer the parameters. We also want to infer their uncertainty, actually. And so that's why I'm writing this down as a probability distribution, posterior probability distribution in the Bayesian language of the parameter y given the data x. This is done by using the training data, right? So you have training data pairs of x and y, and that you feed, and from that you want to infer this posterior p of y given x. Now, we don't typically, or often, we don't have real data to train on. Instead, what we have is simulated data. And so the simulations are there for the training data, and this goes under the broad class of models, which is called simulation-based inference, right? So you don't try to do any likelihood analysis as one would traditionally do, but instead you just have training data pairs x and y out of simulations, and then you try to infer the posterior p of y given x. All right, in some fields this has been very successful, and high energy physics is one example, and we'll hear talks about it later in the week. But in fields like astronomy and cosmology, people are starting to do this, and there's a lot of potential promise, but it's fair to say that we haven't actually yet developed any, or not, at least not too many success stories that are known. But I think it is likely to change very quickly, because I do believe there's a lot of potential for these methods to extract more information than traditional baselines. And I'll talk more about this, in the context of cosmology. Okay, next slide is about discriminative or supervised learning. As I said, typically we want to learn the posteriors of parameters y given x, so that is supervised learning. We have training pairs of x and y, and we will typically parameterize this with some neural networks. And these neural networks may be simply trained on some loss, such as L2 loss. This will give us out just a point estimator. But as I try to emphasize, we want to do more than just a point estimator. We want to get a full probability distribution, because we want to also quantify uncertainties, and that's why we want to actually, ideally get out the posterior P of y given x. Now, when y is discrete, this becomes a classification problem, and so you can talk about cats and dogs, but more often than not, in physical sciences, we have continuous variables, continuous y, and so this is therefore a regression problem. Okay. Now let's contrast this to generative or unsupervised learning, which is learning the probability distribution of the data itself, P of x. Maybe conditional on y parameter, P of x given y, but nevertheless, the task is different here, because we want to get some probability distribution of the data. And so how do we do this? Well, we do this by parameterizing. I'll talk more about how we do this actually, but why do we want to do this? Well, one goal is actually to create new data. Generative models are, well known that you can create new data. We all know that, you can make great ChatGPT or DALL-E pictures or texts using that. And so that's one goal. But for scientific applications, actually, another interesting goal is the likelihood estimation, which is to get this object here, P of x given y. This is the likelihood of the data, conditional on some parameter, y. And then if we have this object here, then we can use Bayes' theorem, assuming some prior on y. Very often this could be a flat prior on y or something like that. Using Bayes' theorem, then we can get back that object that we wanted to get in the first place, which is posterior, P of y given x, using this Bayes' theorem. Okay? So that's another way to get to what we typically care about, P of y given x. But this approach actually gives us two more capabilities. One is, as I said, that it creates simulated data. And the third one is this approach can enable us to do anomaly detection. What does that mean? This would be a generalization of the standard chi-square fitting. And, is the chi-square good or not on the data? Here, the idea is that you look at this density of the data, P of x, and you ask, is this density in a typical set of your training data, or is it perhaps low compared to the typical set? And if it's low, that suggests that maybe this data did not come from a training set, and therefore there's some anomaly in your data that then you need to go and explore further. Okay, so both methods can give you P of y given x. Well, which one is better? Well, opinions differ on this question. Traditional answer is that if you go and train directly on what you care about, which is P of y given x, the discriminative training or supervised training is always better, but perhaps the answer is a bit more subtle, in the sense that it has also been observed that if you don't have enough training data, then sometimes there are regimes where generative training actually is better for a while. Not better in the limit of infinite amount of data. In the limit of infinite amount of data, you always win by doing discriminative learning, but if you don't have a lot of training data, then maybe generative learning actually can win. In this talk, I'll talk about more hybrid approaches where, you may have generative learning task, but you still train, but you then have a hybrid training. First you train in generative and then you train discriminative, and these kind of approaches actually seem to give the best of both worlds. Okay, so this was introduction to what I want to talk about in this talk in terms of machine learning. But now let me first tell you a little bit about cosmology, what we want to do there. Well, we have standard cosmological model, which is a Big Bang model starting from some seeds of initial structure. Seeds come from inflation, and then the universe is expanding and cooling down, and the structures are growing due to gravity. We also have a standard model of what the universe is made of, and it has, a quarter of dark matter, 5% of atoms, and 70% or so of dark energy. So, nevertheless, there are still a lot of open questions that we would like to answer, but with the new data, with new observations. And these tasks might be inference, there might be model testing, maybe you want to test some new model of cosmology, and maybe you will discover something by doing this. The typical questions that we ask are, for example, what's the nature of dark energy? Is it time dependent or not? What's the mass of neutrinos? Is there any new physics in the data? Do we have tensions between different observations that maybe lead to new physics? What is the total matter content in the universe? Are there any transient signals? What are the signatures of inflation? Things like that. All right, so these are all the questions we would like to answer by taking more data. Now, fortunately, we will have, and we already have, a lot of data, and a lot of new data are coming along. For example, on the spectroscopy side, the DESI is already taking data, and there will be DESI-2, SPEC-5, and so on. So there's a lot of galaxy spectroscopic surveys that are coming online. Similarly, in the imaging domain, there are ongoing surveys such as HyperSupremeCam and future surveys such as Rubin Observatory or LSST. Euclid has already launched and is already taking data. There will be Spherex. Then slightly further down the line, there will be Roman telescope. So there's a lot of these telescopes and surveys that are going to be taking data. And finally, in the CMB, Cosmic Microwave Background world, there's the Simons Observatory, South Pole Telescope, and so on. Okay, and here are just 3 examples of these kind of surveys, DESI, LSST, or Rubin, and CMBS4. And so this is really, in cosmology, there's a huge investment in terms of new data. For the most part, the data analysis is actually very simple, and it's only based on the 2-point correlation function. So this is fine if you have Gaussian distributed data, which we believe cosmic microwave background is very close to a Gaussian. And so in that case, we're extracting most of the information from the data. But when you look at an image of galaxies like that, and that clearly, is not a Gaussian distribution. And so there's more information in the data than it is in the just 2-point functions, such as correlation function or the power spectrum. And so there's a lot of proposals for additional summary statistics to do. Like, you could do bispectrum, you could do Minkowski functionals, peak counts. I mean, there's a long list of T's, right? A lot of papers out there. But the question is, how do you go about it if it doesn't make sense to just do all of them, and how do you combine them and so on? So it becomes very unwieldy because the summary statistics are actually very high dimensional in the end if you just want to combine all of them. And you're still not guaranteed to have all the information. So basically, these new data require new data analysis that can handle, first of all, very large data sets, and second, they can extract the full information that is in the data. And so the question is, can we capitalize on the recent successes of AI and statistical inference? And the answer, I believe, is yes. But can we take off-the-shelf AI ML code to do so? The answer is, for the most part, probably no, because the data dimensionality is very high, and because we have a very stochastic nature of the data, and we have symmetries in the data and things like that. Okay, so there are some modifications that are needed if you want to extract full information from these data sets that I'm talking about here. All right, so what do I mean by stochastic and high dimensional nature of cosmology data? Well, these would be typical, I don't know, let's say maps of projected dark matter that are, not sort of a good proxy for the weak lensing data. I'll tell you more, I'll show you more later how we generate the weak lensing data, but basically this is a rough idea. And so you see that you have a lot of structures, they're completely stochastic, there's no value in where they appear, but they are, but they are very noisy in some sense. They're also very non-Gaussian. You see some filaments here and voids and things like that. Depending on the type of data you have, they could also be very high dimensional. If you have a pixelized or voxelized data, I mean, for pixelized data for two-dimensional maps, it's not unusual to have millions of pixels. For three-dimensional maps, then it's not unusual to have actually tens of millions or billions even. So the training is also very expensive because we need to run n-body simulations to generate them. And it's very difficult to interpolate between these data sets, given that we have just a finite number of training simulations. And so our approach is, that I'll discuss here, is that we'll first learn the data structure using generative learning, and then we will follow by generative plus discriminative learning to reach optimality in terms of the summaries, in terms of the posteriors. Okay, so let me now focus on the specific application here, which is weak gravitational lensing, and where we'll have a specific method, with normalizing flows, which will apply to the weak lensing data. Okay, so what is weak lensing of galaxies? Imagine you have background galaxies. And the light travels through the universe from these galaxies, and it's being deflected by the mass along the line of sight, right? So this is a standard thing that already Einstein predicted, that matter deflects light. And if you observe this with, for example, something like Rubin or SST, you may start to see distortions in the galaxies. Okay, so imagine that all the galaxies were just have the same shape, then as this light travels through the universe, then they become distorted by the intervening matter, right? And what matters here is some kind of it's a projection of the dark matter along the line of sight with a specific weighting kernel. And this is what this projection would look like in a 2D projection. This is what we call this convergence map or kappa map. Okay, and you see, again, this kappa map has these peaks, which are, dark matter halos, has voids and stuff like that. So this is, a projection of the dark matter along the line of sight. So we observe this, we want to reproduce this, and then from this, what we want to get to is the cosmological parameters. All right, so how do we do this? Well, okay, before I say how we do this, what is the goal? I already mentioned the goal, but we want to extract maximum amount of information. Now, one way to do this is to do a full Bayesian inference, where one can actually write down the full likelihood of the data and so on and so forth. And then, but the problem is that one needs to sample this full likelihood over the initial conditions of the universe, and this could be a billion-dimensional parameter space that we need to sample over. This is a very challenging problem. People are trying to do this, but this approach. As I said, it's very challenging, and so I'm not going to talk about it anymore here, even though we do work on it. So here I'll talk about more about what machine learning approach, right, which is to get this posterior P of y given x. And specifically, I'll talk about our approach, which is to learn first the P of x given y, use a generative model, and then using discriminative training to invert this to get to this. Okay, so why do we want to do this? Clearly, there are cons of doing this, P of x given y, because x is very high dimensional. X is that two-dimensional map that I've shown you before. And so this could be easily a million-dimensional map, for example. Okay, so, but we'll try to make this problem easier by using symmetries and by using multi-scale information multi-scale decomposition of the data. And we'll approach this with normalizing flows, which I'll define in the next few slides. But before I do that, let me just say a few words more about how we generate the data here. So we run an n-body simulation forward in time. So we start from initial conditions, which is a Gaussian field. Then we run it through an n-body simulation, and some gravity clusters these structures, and we get to this. And then if we need to generate galaxies, we also need to map from the dark matter to the galaxies. Okay, so this is traditionally very expensive, but newer simulations that we have been developing over the years can make it a lot faster. So they go under different names, but these simulations are these days a lot faster. Like they can easily be actually minutes or so, and so we can generate a lot of them. Now the problem is we need to also generate many of them, because we need to project we need to do ray tracing through these simulations. And so the way we do this is we slide these simulations up, we then randomize these slices, and then we project the rays along the line of sight, and we deflect the rays. So the rays are not straight, but we deflect them because that's what light does, right? Matter deflects the light, and so that's why we are not projecting these along straight lines, but more along these kind of deflected lines. Okay, this is called ray tracing. And so here we need to have several simulations, and they also need to have several different resolutions, because you see here close to us, we need high resolution, and so we need to have small simulation boxes, but high resolution. And further away from us, we can get away with lower resolution but larger simulation box. Okay, so here's an example, right? This would be a slice very nearby. You can see there's a lot of structure, very nonlinear structure, and this would be a slice further away, right? So you can see it's a lot larger scale, more Gaussian and things like that. But we have to project all of these slices to get the final map. And then finally, what we need to do is also we need to add realism of an actual survey. So this would be an example for hyperspring cam. You see, basically, it's I forget what, it's 60 degrees wide, long, and I don't know, 10 degrees wide. And this is a survey mask, which is ugly, but moreover, you also see a lot of holes. Those are the stars that are too bright, and we cannot remove them from the data, and so we just need to excise them out of the data. So these masks are pretty ugly. Okay, so now once we have this, we have realization of the data, one realization of the data. Now we can do this, and we need to do this many, many times. So we have a lot of training data. So we will typically do this 1,000 times for one set of simulations. And we have about 100 simulations where we vary cosmological parameters. Okay, so these are our cosmological parameters. Could be, as I mentioned earlier, could be initial density, amplitude, could be matter density, could be neutrino mass, could be dark energy, and stuff like that. Okay, so now we have the training data, which is of order of 100,000 maps. So now we will train a normalizing flow, a specific form of a normalizing flow on this kind of data. So what is a normalizing flow? It's a mapping from a simple distribution like a Gaussian to a complicated distribution. So the way one achieves that is that at each step of the map, at each map, you do some very simple transformation. Why very simple? Well, the reason it needs to be very simple is because it needs to be invertible. So we need to know not just f from one step to another, but also inverse f. And we also need to be able to compute this Jacobian, so df over dx determinant, so that we can evaluate the density. So if we have both of these things, then we stack them together, many different maps. Now, this plot, of course, is one-dimensional, but reality, as I said, we can do this in millions of dimensions. We need to do this in millions of dimensions. Okay, how do we train it? This is maximum likelihood training. Basically, you want to maximize the likelihood over the parameters of your network, with which you parameterize your normalizing flows. And so, for example, again, a simple example, let's say you have this map F. Let's say your data like this, you want to map this to a Gaussian. Initially, you'll get this. So this is not the result of the optimization, but after you have optimized, right, you obtain this map F, which is this, which maps now this distribution to a Gaussian. All right, this is a result of maximizing the likelihood of the data. And so now you have achieved a map from a complicated distribution to a Gaussian, and then you can also go the other way around. Okay, so for physics, at least for cosmology, we have to use other things in order to scale it up in dimensionality. So we want to be able to do spatial structure modeling. For example, we certainly want to do symmetries, at least translation. So for translation, it's relatively straightforward. We just need convolutional neural networks. Rotation is typically, I'll talk about in our model, not going to be implemented, so it's only approximately implemented. But then you need to also be able to learn from very stochastic data, and you need to have spatial structure modeling. Okay, and so let me just give you one example, this multi-scale flow, where we decompose using wavelets original map into coarse grain map, and then three different maps, right? So this still has the same number of pixels. And then we learn these conditional dependencies of this map, basically this one is this one. So it's a joint probability distribution of this and this, a given y. But now we keep decomposing this one because we have now coarse grain this one. But now we can coarse grain it again to 64 and the difference maps, right? But I guess the only issue here is that we have all of these conditional dependencies that we are picking up along the way. So these are very high dimensional conditional dependencies, which are hard to model. Nevertheless, with neural networks, with the smoothness of neural networks, you try to model them as well as you can. Okay, so this is the idea of this multi-scale flow. And here is one application. The first application is that once you train, you can now have new ways of generate simulations. In this case, you generate weak lensing maps directly. So this would be an example of this. You go from coarse grain, low resolution to high resolution, and you can see that this one is very similar to the one that I've shown you before for the training. Now, in terms of statistics, this map, has identical power spectrum and identical one-point distribution function as the regional training data. So it's a pretty good result in terms of the training. Okay, next is the main task, which is a reliable and high quality, ideally optimal posterior analysis, so inference. Here I'm showing a result of different scales. So one advantage of doing this multi-scale is that you can actually now learn the likelihood as a function of scale. And you can actually do this posterior analysis at each scale. And so this is shown here at different scales. I'll get back to this on the next slide, but you can see basically, the coarse grain scale, this is a green, has very large contours. And then the relative to the final, which is the full likelihood, in this case, we went to 512 square. So this is a 250,000 dimensional normalizing flow. And you can see basically that as you go to smaller and smaller scales, you can pick up more and more information. Here I'm showing amplitude of fluctuation sigma 8 and matter density omega matter. Okay. And here I'm showing 20 examples. And again, I want to emphasize that we are doing posterior analysis. We have the likelihoods, right? But we are inverting these likelihoods using Bayes' theorem to get the posterior. And so an important question is, do you have correct coverage? All right, I guess we can debate about Bayesian versus frequencies, but even if you are Bayesian, in this context of machine learning, of these black box approaches, you need to convince yourself that whatever comes out of the analysis is a reliable uncertainty quantification. And the way to do this is just to try this on many different out-of-sample examples and make sure that your frequencies are correct. So if you claim 95% contours, you better have only 1 out of 20 to be outside that 95% contour. And if whatever your 68% is, you better have only roughly 1/3 of these 20 maps to be outside 1 sigma, right, 68%. So this is quantified typically with this coverage map, which is where you plot the predicted number of models within your contour versus the actual empirical coverage, how many you have. And so successful models have good empirical coverage by being along this line. All right, so you can see ours here is very close to this line. If it were in this corner, then it would have been conservative. What is particularly a big problem often in machine learning is that machine learning models are overconfident, in which case they are here, in which case you are underestimating your errors, okay? But this model is giving us pretty good results. Okay, so that's good. So we have accurate prediction of our posteriors, we think. Next question is robustness, or are we getting robust results in terms of unknown unknowns? Anomalies. Okay, so we have two ways to go about it. One is to look at multi-scale information, because very often, if there are anomalies in this cosmological data, they come at they're more important on certain scales versus other scales. Typically, they will be more important on small scales, but not so important on large scales. And so if you have, these different scales here, right? If there is no problem, then they'll all be consistent with each other. So that would be the analysis here. On the other hand, if you have something unknown in the data, for example, let's say you just got your noise wrong, then maybe you have no problem on large scales, because noise doesn't matter very much on large scales, but you have a problem on small scales. Okay, and so you see that basically you have inconsistent posteriors between different scales. So that will be an indication that something is wrong in your analysis. Okay, so that's one way to identify unknown unknowns. Another way to identify unknown unknowns is, if you have a generative model, is to look at that density estimator that I mentioned, P of X given Y. You can maximize this over Y so that you have the highest possible density. And then you ask, is this still in the typical set of your training data or not? And so here is an example that we have tried, again, as a function of different scales. We have tried we injected an anomaly, in this case, baryonic effects in the weak lensing, and then we analyze it by using only dark matter simulations, which don't have baryons. And so we know, well, I mean, and we pretend that we don't know about the existence of baryons, and the question is, can we identify it? And this is, this plot that shows you false positive rate versus true positive rate. And basically, the point of this plot is, if you're along the diagonal, then you're not doing very well. And the best you can do is this kind of square corner. And the problem with this kind of test is, well, it also depends how much anomaly you have injected and things like that. The point I'm trying to show in here is that this method does have sensitivity to these anomalies, such as baryonic effects, because the results are not like this. The only place where the results are straight line are the largest scales. Larger scales are not sensitive to baryons, and so it's not surprising we have no sensitivity to baryons. But then as we go to smaller and smaller scales, we see we get more and more into this corner, which is where we want to be. Basically, we are able to identify anomaly using this unsupervised density estimation. And so that's again one of the few ways that one has to identify unknown unknowns. And because unknown unknowns are particularly problematic, because you don't know they exist, it's always worth looking at these things. And so this is an advantage of generative learning, right? Of learning the likelihood P of X given Y. Okay, so the question is, how much better is this multi-scale flow versus standard power spectrum analysis? Here is an example of one of our simulated analysis. Again, there are no data here yet. In terms of these two cosmological parameters, sigma 8 and omega matter, power spectrum gives us a lot larger contours than we get with this multi-scale flow, up to a factor of 10 in terms of the area. All right, so we'll have to see if this claim survives, the reality of the data. All of the systematics here yet in this analysis, but certainly it looks very promising in terms of giving us a lot more statistical power for spectral analysis. And I want to also emphasize that this approach appears to be better than some of these other alternative methods that have been applied to this kind of cosmology data, such as scattering transforms. Okay, so what are our future plans? We need to add more complications from the real data. So we are working on adding intrinsic alignments. We're working on adding baryonic effects. We're working on adding photometric redshift uncertainties. And so our immediate goal is to finish hypersupreme CAM year 3 analysis, which is a really nice data set that is well suited for this because hyperspring-cam is very similar to LSST, to Rubin. It goes to very small scales, has a high density of background galaxies. And so it's where we believe there's more information to be gained because it's such a nonlinear regime where, power spectrum doesn't extract all the information. So we're looking forward to finish this analysis. And then, of course, once this is done, one should think about how to develop the pipeline analysis for larger surveys such as Rubin and Euclid. The challenge with this is that we are already at the limit in terms of our N-body simulations. The HSC fields, as I've shown you earlier, are of order less than 100 square degrees. But the future data will be thousands or even 10,000s or even more, 20,000. And so we need larger simulations while still preserving the resolution that we have. And so this is a challenge for the future, basically, in terms of scaling up the N-body simulations. Okay, so my summary, therefore, is for cosmology, in terms of AI for cosmology, well, we can do 3 tasks that I emphasized: simulating new data, anomaly detection, and inference, statistical inference. I didn't mention so much this, but combining, yeah, okay, I did mention, I guess. I want to emphasize, right, that generative learning, especially if you have this density estimator P of X given Y, it does give you more information. And so if you can apply it and get similar results to discriminative learning, then one should do it. You pay the price in terms of, training, in terms of, these architectures of normalizing flows, of restrictions on normalizing flows. But at least in our experiments, we have found that we have not seen a performance loss. In fact, maybe just the opposite. Maybe these generative models actually also work better in terms of posteriors, the widths of the posteriors. And then finally, we believe that these kind of approaches are promising in terms of weak lensing applications for the future data, up to a factor of 10 in terms of figures of merit. And so certainly they should be deployed to the real data to see what their reach is. In terms of general comments for science, I would say, well, every field is different. It's very hard to generalize anything from one field to another. So certainly success is not guaranteed. But still, there are many fields where AI has at least the potential to significantly improve current baselines. And so obviously, this is the point of this workshop, to explore where AI and machine learning can be applied in terms of physical sciences and other sciences. And I guess I'm looking forward to more discussions about that. Thank you.
Great, thank you, Uroš. I think it's a great effort to make it accessible, I hope, to wide audience. Questions for you?
Thank you. Yeah, thank you for this very nice talk. So like on slide 30, you showed the calibration, and I mean, I fully agree, like this is an important thing to do. Like, so what I wonder is, yeah, exactly. So what I wanted here is, okay, so a calibration, I mean, shows you basically that you get like trustworthy results, right? But so like my question is, how can so this optimality aspect, right? So kind of how can you make sure that like, in 2 years you couldn't come up with like a better sort of normalizing flow that gets even tighter posteriors, right?
I mean, at some point, this the point here is, what is this called showing? It's basically, let's say you reject some events, like when you reject some threshold of intensity, and you ask them how many are even if you reject maybe some false positive rates, let's say 10%, right? How many of true positive events you're also rejecting by doing that, right? And so that's why, ideally it would be here, you will be here, right? Where, well, you're not rejecting, maybe rejecting all of the false positive rates and you're accepting all of the true events, right? That's why I'm saying this is the ideal case. But obviously we have, noise in the data. And maybe what we're injecting is not even distinguishable from the true data. So that's why I'm saying I don't think it's possible to be perfect in every situation. What I was trying to show with this plot is, well, we are getting something right here. We're getting some sensitivity to this particular anomaly, which in this case is a systematics in the data. Sorry, astrophysical systematics, let's call it.
Okay, thank you.
Thanks for the nice talk. I just have a bit of a technical query. So I guess if I understand correctly, the way this training procedure is going on, you have this n-body simulation map, and then you have train a flow-based network, which is basically doing the generation and discrimination simultaneously, right? And it's going on the same go.
So you're talking about training or the
Yes,
follow-up?
yes. I am, yes.
Training.
Right.
Yeah, I didn't say actually much about training. The training is hybrid. We first train on maximizing the likelihood,
Yeah.
but then we switch to train on maximizing the posterior.
That's right. So,
Yeah.
so the way I would like to think about this, let's say another counterpart would be something like a GAN, right? You have the generator and discriminator running simultaneously. So I have never trained a normalizing flow, but training a GAN could be extremely complicated, like just some small shift in the data, small noise could just completely destabilize the network. Do you face some problem here?
No, but this is not, again, would be a generative model, right? It would be under the task of generating, well, generative model. So maximizing likelihood. If you have a normalizing flow where you can compute the density, then you can do maximum likelihood, right? You cannot do this with GANs because they're not normalized and all of that. So, so that's just a question of how you do generative part. But here we want, as I said, we want to have both generative part, P of X, maximizing P of X given Y, but we're also maximizing P of Y given X. And so our loss, actually in the end, our loss is a sum of the two losses. Well, sum of the logs, I guess, right?
First of all, thanks, Uroš. This is an excellent summary and a talk. I have a question actually about something related to this slide. So I'm going to oversimplify this massively, but what you're doing with normalizing flows is essentially constructing a map from the very early linear regime to the highly nonlinear kind of regime that's closer to present. So those weights in the network have some information about the physics that takes us from the nonlinear regime, linear regime to the nonlinear regime. Basically, what we would usually do through n-body simulations. How much work is there to try to understand, to try to look at that latent space and see what is this telling us about the complex n-body physics?
Telling us about what?
What is this telling us about the complex n-body physics?
Oh, yeah.
Because you're essentially somehow the network learns what an n-body simulation does, and it's got to have some interesting information just on n-body dynamics in effect.
Yeah. So okay. So the question is about the observation is that an n-body simulation also takes us from a Gaussian initial condition to the final field, and therefore can also be potentially interpreted as a normalizing flow. Now, in principle, there's an infinite number of ways to go from a Gaussian to a distribution, right? So just the fact that n-body is one of them doesn't mean it's the one that also happens here. In practice, actually, we didn't look at it in the context of this flow, but we had a previous flow called translation rotational equivariant normalizing flow, and there we actually looked at the cross correlation of the Gaussian field with initial conditions, and we found actually very high correlation, right? So there is a high correlation, but it's actually very difficult to train it so that the correlation gets better. Now, the reason why this becomes less useful is actually the masks, right? Once you have a mask like this, then you're not getting really the initial conditions, right? Because you're missing, basically half of the area, and so at that point, this correlation becomes less useful. So yeah, but it's true that in principle, and people have been pursuing reconstruction of initial conditions using machine learning, right? So maybe that's closer to what you're getting at, where you can actually write down losses, where you're minimizing the literally the difference between initial conditions and the reconstruction. That is typically done in 3D though. These are 2D projections, right? So it's in 2D projections with all the mask and all that, it's very difficult to make a connection to initial conditions.
Thanks. Anybody else? Maybe just a naive question. You mentioned that for next generation observations and body simulations become a problem, right? The scale. How about accelerating the simulations with
Accelerating simulations.
right, like what I mean, I know there is also push to make faster, to make machine learning like,
Yeah.
simulations.
Well, okay, so
Matters.
I guess once we have created this machinery, generating new simulations is extremely fast. So at this point, this is negligible. So in that sense, this is definitely accelerating the
Right, but this is with Lansing. I'm saying the dark matter distribution simulations. Are those
training data, you mean?
The training data, right?
Yes. I didn't discuss too much detail, but I did mention, these codes here that we have developed. These are fast n-body simulations that, of course, we check that they are sufficiently accurate. But very often, for example, if you take FastPM, this one has 10 to 40 time steps, right? Traditional n-body simulation will have thousands of time steps, but it turns out you don't need thousands, you just need, a few dozen. So that's an example and then we have ported these to TensorFlow and JAX, and these are these two versions. So basically, there's development in these codes, and they are getting faster, which is why I mentioned, earlier that this can be minutes, right? And this kind of simulation depends on what kind of box sizes you have, right? But there's certainly been a lot of development in terms of accelerating the n-body simulations themselves, yes.
Okay. Oh, Marco.
Yeah, thanks. So yesterday we started a little bit with this general discussion in machine learning, whether it is useful to inject knowledge, like physical knowledge here, or the problems will be solved, like many people in machine learning think, just by adding more compute and more data and so on. So it seems that you are implying that in physics, at least, the knowledge is very essential.
I wish. I wish I implied that. Well, yeah, it's a sad story, I would say, where let's see, where do I have? We developed two normalizing flows. I had them somewhere. The original, the first one we developed was the translational rotational normalizing flow. Rotations are usually not implemented, right, in the architectures. And so we thought, well, we have rotational symmetry in our cosmology data. Let's put it in explicitly, and we did. And we thought it was great and all of that. But it turns out it was not sufficiently expressive, and we were not able to actually get accurate results for big maps. So unfortunately, we actually removed the rotation part of the architecture and then we went to this multi-scale flow. Okay, so that's just one example, right? Now, I do know that people in, I don't know, lattice QCD and stuff like that, they do put in various symmetries, various group symmetries, and they are getting a lot better results. So certainly, it depends on the application, depends on the architecture, but it's not as simple as just saying, well, if you have some symmetry, you put it in, you'll get better results, right?